Great. Well, of course, I'd like to begin by thanking everyone who's helped organize this. I'm really sad that I can't be with you in person. Originally thought I wasn't going to be with you in person because I move in a week, but turns out the real reason I can't be with you in person is because I've caught COVID. So, silver lining to that, I guess. I'd like to talk today about sort of the 10 years, which includes a little bit of the future of super bubble feedback, the kind of next generation, excuse me, feedback model for in-body shop codes. So I'd like to sort of begin by motivating this a little bit by talking about a kind of important and maybe a bit underappreciated paper that was published 10 years ago, the Aquila Comparison Project. So this project aimed to see whether or not the currently existing state-of-the-art cosmological simulation codes of 2012 could actually reproduce both the Milky Way that we see and reproduce each other. But what was found was that for both the stellar mass to halo mass relation for these galaxies and their rotation curves, uh, none of these simulations really agreed with each other. And really importantly, most of them disagreed quite significantly with the existing observational constraints at the time, which really only have become stronger since. So in particular, almost every simulation was producing too many stars for the size of the galaxy, the halo mass that they were simulating. And these galaxies tended to have strongly peaked rotation curves, indicating that they were forming most of these stars within the bulge. And so this caused a lot of groups, ourselves included, to start rethinking what might be missing here. And the main thrust that most people have started looking at was how we model feedback. And the reason we have to model feedback at all, the reason we can't just let the hydrodynamic solver itself kind of sort things out for us, is a matter of resolution. So we can never, within our lifetimes, get to the point where we're resolving every single atom, but of course, that's not as far as you think you'd need to go. We really can't even get to the point where we're resolving individual stars or even individual small open clusters in cosmological simulations of Milky Way mass galaxies. And what this leads to is this problem where if you say take the energy of a single supernova and deposit it into a particle or a gas cell, you're going to heat it up, but not heat it up very much. So if you say take a supernova and put it in a 50,000 solar mass gas particle, you're only going to raise that gas particle's temperature to just under 100,000 Kelvin. This means at typical ISM densities, you're going to cool away. This is the cooling time here on the y-axis. You're going to radiatively lose all of that energy in a few thousand years. Only if you were able to get to resolutions of a few hundreds or perhaps even a few tens of solar masses are you going to get to the point where the injection of a single supernova is going to result in gas that's hot enough that it can do things before it's lost all of its energy due to radiative cooling. So this has typically been called a numerical overcooling problem, but what it really is a numerical overmixing problem. You're taking the heated ejecta of supernova and putting it into too much gas. So the classic approach that's been taken in in-body shop codes, gasoline and chaga, has been using this blast wave feedback model. This was a model developed by Greg Stinson, and it really attacks the problem directly. If you're cooling too much, simply shut off the cooling where it's a problem. And you can calculate that cooling shutoff using some classic equations from the McKee-Ostriker 77 ISM paper to determine how long you should shut that cooling off for. And this has been used a lot. I mean, the paper itself has over 600 citations. It's been really foundational for a number of really, really important simulations. But it has some shortcomings. In particular, Greg Stinson ran in 2010 a set of cosmological zoom-in simulations, that MUGS suite that James had earlier talked about. It's really designed to match the sort of kind of galaxy we would see around Milky Way mass, so around 10 to the 12 solar masses. And if you look at the stellar mass to halo mass relation of the MUGS galaxies, you can see that every single one is above by a significant amount the uncertainties within the stellar mass to halo mass relation we expect from observations. And on top of that, the circular velocities, the rotation curves of these galaxies show, and if you do a bulge disk decomposition as well, you can see this, that these are really bulge-dominated systems. So that same issue that had been identified a few years later across the spectrum in the Aquila comparison project. On top of that, there are a few numerical forms. For one thing, you can run into a situation where the cooling shutoff time that's calculated can be very, very long, hundreds of mega years in some cases. And this really isn't physically reasonable. If something has its cooling shutoff for 300 mega years, it should have either broken out of the ISM or really radiated away all of its energy by that point. There's also another issue, not directly related to the feedback model, but has to be addressed as well, which is that if you look at the gas particle masses, this should be a log gas particle mass in the MUGS simulations, you can see the initial particle mass here of a couple by 10 to the 5. Gas particles that have lower mass because they've spawned star particles. But what's kind of scary and problematic is we have this long tail here of gas particle masses all the way out to about 1,000 times heavier than the initial particle mass. And this is coming from hundreds, thousands of star particles depositing their feedback ejecta into single gas particles, raising that mass by a significant amount. And SPH, as a hydrosulfur, does very, very poorly when gas particle masses are not near equal. So even offsets by about a factor of 10 can be a problem. And you can see here we're getting up to factors of 1,000. So this isn't directly related to the blast wave model in particular, but it's something that needs to be fixed. And we fixed it now with split gas, where gas particles can actually fission once they exceed a certain fraction of their initial mass. There's also some kind of more conceptual issues here. For one thing, this shutoff time is calculated instantaneously when feedback is injected. And because it depends non-linearly, it doesn't go as the supernova energy to the power of 1, but to the power of 0.32. It means that if you have the same amount of energy being injected by one particle versus two particles, you'll calculate different cooling shutoff times. So in other words, it's kind of explicitly unconverged. As well, because again, that calculation is done instantaneously when the supernova detonates, you don't have any ability to see later on effects. You calculate a cooling shutoff time that depends on your density and pressure only at the moment the supernova goes off. And so later things that could maybe expel that gas from the galaxy and therefore change these cooling times can't really be captured in this. So we kind of wanted to rethink what we want in a feedback model. So the first thing, of course, is we want to be able to make good galaxies. We want galaxies that match the observed scaling relations as best as we can. We also want reasonable supernova energies, so 10 to the 51 ergs per supernova or less. And in fact, if you look at sort of the current literature of stellar evolution modeling and core collapse supernova modeling, 10 to the 51 ergs is probably already a bit of an overestimate. We also want to be able to run with the full suite of metal line or H2 cooling. So we don't just want to cool the low temperature gas with metal lines, which you get with the Cool Cosmo define for those of you who run N-body shop codes. We want to be able to cool all of the gas in a self-consistent way. And of course, also we want good numerical convergence, realistic gas behavior in the density temperature plane. So this kind of pushed us towards designing a model that's not star-centric, that doesn't work from the perspective of the star injecting the feedback, but instead a gas-centric model, where since gas is the thing that feedback is done upon, we want the gas to be the thing that is doing the calculations as part of the model. So the first thing to think about with this, of course, is what physics is involved here in setting the supernova heated mass, because as I mentioned at the beginning, this is really an overmixing problem. So for one thing, we know that supernova feedback because star formation is clustered, feedback itself must be clustered. Those individual supernova bubbles will rapidly merge, forming a larger superbubble that's driven much more by a wind-like model than a blast wave-like model. So to model this, we built three simple pieces that combine to form the superbubble model. The first is a thermal conduction component that moves energy within this hot bubble. The second is a stochastic evaporation. Because that thermal conduction can heat the inside of this shell, it can then drive a mass flow that evaporates it. And finally, for the earliest stages of feedback, when the bubble itself has very little mass, much less than a single gas particle, we allow it to become two-phase so that this cold swept up shell and hot bubble can be tracked separately without mixing them together and giving you, again, this overcooling problem. So the conduction part is fairly simple. It's governed by this simple conduction equation, which if you see you've got two nablas in here, means that this is like a diffusion equation. So we can model it in the same way we model thermal diffusion. But because you see there's this 5/2 power of temperature, it means that the conduction and also therefore the evaporation is self-limiting. If you increase the temperature of the bubble, you'll rapidly increase the amount of evaporation and kind of push you to a self-regulating temperature. But to actually model that evaporation, we don't have the resolution to capture the interface, that thin feedback front where that evaporation occurs. So what we need to do is analytically calculate the amount of mass that should be evaporated through thermal conduction, and then turn that mass flux into a probability to convert a single discrete particle from cold to hot. We do this in exactly the same way that we turn a mass flux for star formation, the star formation rate, into a probability of forming a discrete star particle. And finally, for the earliest phases, we need to be able to split a particle into two phases. So this hot bubble and this cold shell. This allows us to actually cool these things, so we don't actually shut off cooling anymore. But because they each have a separate temperature and density, they're calculating cooling rates that are much more realistic. The way we're able to get these separate temperatures and densities is by assuming the cold shell and the hot bubble are in pressure equilibrium. That lets you turn the pressure of the particle and its internal energy into a density that can then be used to calculate the cooling rates. This ends up giving you gas that behaves realistically from what you would expect from your physical intuition. So a galaxy will have a warm neutral medium that cools, forms stars, and then feedback from those stars can then heat gas up to high temperatures where its cooling is relatively inefficient. And if you look in a cosmological simulation, you can see that as gas moves away from the galaxy, from this cyan to blue to yellow, it's actually more or less moving along an adiabat, a line of constant entropy. In terms of convergence, the model works very well. So in the isolated Agora disk, you can see after an initial starburst, because the system's out of equilibrium, you end up settling to a star formation rate of about 1.5 solar masses per year across all of the resolutions we tested. So across a factor of 100 change in baryon resolution. What this ultimately does when you start putting it into cosmological galaxies is pretty interesting as well. So in terms of how rapidly these galaxies will form stellar mass, they're within the bounds that we would expect from abundance matching across cosmic time. Whereas previous runs, this is the same set of galaxies as in that MUGS set of simulations. With blast wave feedback, you end up overproducing stars really from before redshift 3. And again, you end up looking at the rotation curve and finding that once again, blast wave feedback tends to overproduce bulge stars, whereas superbubble feedback can give you a disk-dominated system much more in line with the Milky Way and other local disk galaxies. The reason for this, though, is quite interesting. It turns out the key component here is actually the way outflows are driven. So if we look at the outflow mass loading, that is the ratio of the outflow rate divided by the star formation rate. It's a dimensionless number, therefore. You can see that superbubble feedback gives you significantly higher mass loadings at high redshift compared to blast wave feedback. Outflow mass loadings of around 10 compared to around 1 or lower for blast wave feedback. And this is really important, not just for regulating the amount of gas that can feed star formation, but also for building disk-dominated systems. If you split those outflows into gas that is low angular momentum, shown here in the solid lines, versus high angular momentum, shown here in the dotted lines, you can see that the high mass loadings at high redshift come primarily from low angular momentum gas. And in fact, the high angular momentum gas that is accreted later is also ejected much less efficiently than this low angular momentum gas. This ultimately means that you're throwing out the bulge forming gas more effectively than the disk forming gas, allowing you to still make a thin stellar disk without overproducing stars within that central bulge. And with this, we can actually start now asking questions in more detail about how this feedback-driven outflow process works. One of the big questions in galaxy formation and cosmology is, why is there this sort of magic mass scale where in the Schechter function of the number of galaxies we see in the universe as a function of their halo mass or size, we see a knee? And why in the stellar mass to halo mass relation that compares how many stars are within a galaxy as a function of their total halo mass, we see a peak. The standard explanation for this is, well, at low mass, supernova feedback regulates galaxy formation, but at high mass, AGN feedback regulates galaxy formation. Now, if this was some other physical process, then we wouldn't need an AGN model. We would be able to model our galaxies only with a supernova feedback model and still reproduce these features, this turnover in the stellar mass to halo mass relation. But we find we can't reproduce these features, which is good evidence that this canonical picture of supernova regulating low mass galaxies and AGN regulating high mass galaxies is correct. We see that as soon as we exceed halo masses of around 10 to the 12 solar masses, stellar feedback fails to regulate the star formation in these galaxies. We, in other words, massively overproduce stars relative to the observed stellar mass to halo mass relation. And we overproduce those stars again in the bulge. We end up having peaked rotation curves in bulge-dominated systems. And what this comes down to is how these outflows actually work. So you can see the outflow mass loading here as a function of halo mass, whether you're looking at the galaxies that produce the correct amount of stars in yellow or overproduce stars in blue, has the same relationship as a function of halo mass, which is flat and high around 10 or so, until you reach a halo mass of about 5 by 10 to the 11, at which point it starts to fall through the floor. And the reason for this ultimately, again, comes down to the way these outflows evolve. It's ultimately because these outflows are buoyant, evolving along that adiabat. And if you're interested more in how that works, take a look at a paper I wrote in 2020 showing how that works. But superbubble feedback is a public tool. I don't want this to just be the Ben Keller talk. So I want to highlight now quickly a few results that other people have been able to get using superbubble feedback in n-body shop codes. So the first result to come out using superbubble feedback that wasn't run by me was done by Lucio Meyer, looking at this question of whether high redshift clumpy galaxies can be used to test different feedback models. In other words, are the clumps that form in these gas-rich high redshift galaxies sensitive to feedback? And he found, in fact, they're very sensitive to feedback. So moving from using blast wave feedback to superbubble feedback, you can see you have much fewer high mass clumps here. These clumps tend to be much shorter lived and lower mass. They tend not to be bound. One of my favorite uses of superbubble feedback was using the MUGS-2 simulations as a kind of blind test for a statistical and observational technique. This tool that was developed by Gwen Eadie is designed to use orbits of satellites and globulars to measure the mass profile of galaxies. And so she was able to take unlabeled samples of orbital parameters from halo or from satellites in the MUGS-2 sample and test whether or not she could reproduce the actual mass profiles without knowing what the right answer was. And you can see that the method does pretty well. You can reproduce quite well the total mass, especially out at high radii, even without doing any kind of fine tuning that you might do if you knew actually what was going on here. This is a good validation that this thing will work for observational data. Gindali Joshi was able to use the superbubble model to look at how accretion onto groups can strip dark matter and gas out of accreted satellite galaxies and ultimately quench the star formation within them. A group in Australia used, again, superbubble feedback to examine the growth of clumps in Milky Way mass progenitors at redshift 2. One of the really interesting things that they found, surprised me at least, is that the observational constraints aren't really good enough to do much in the way of constraining feedback models. Even in galaxies without feedback, you're still more or less on some of these clump scaling relationships that have been made from observations like Dynamo. You can see, though, that superbubble feedback, as with before, makes smaller clumps. And also, this x-axis here shows the disk's velocity dispersion over its rotational velocity. You can see since we're down near zero, these are, again, much diskier systems. Really exciting work coming out of Samantha Benincasa has been to add in additional forms of feedback in terms of FUV heating on dust grains. What she found is that FUV heating alone can't regulate the star formation within Milky Way mass galaxies, but it may be really important for this mixture of hot and warm ionized and warm neutral gas. So in other words, getting the correct ISM phases may depend on how you treat your FUV heating. And finally, most recently, Mattia Mina and Siqing Shen here in Europe have looked at resimulating a set of dwarf galaxies using superbubble feedback with an eye to the circumgalactic medium of these things. And what they found is that the CGM of simulated dwarf galaxies contains much more metals than the CGM of galaxies simulated with blast wave feedback. So you can see here in green for carbon 4 or oxygen 6, we have a much higher column density of these observable metal lines than in simulations run with blast wave feedback. Closer, and not in perfect agreement, but in better agreement with the observational constraints. So for the last couple minutes, I'd like to talk to you a little bit about where I think the future of feedback in the N-body shop and beyond is going. So currently, I'm working on the superbubble volume. We're calling it Amarok. This is a resimulation of Romulus 25 with superbubble feedback and full metal line cooling. So the original Romulus only had metal line cooling for low temperature gas. This includes all gas. You can see here for the stellar mass to halo mass relation at redshift 2, we're in a little bit better agreement with the observational constraints from abundance matching, and our star formation rate density is in excellent agreement with the cosmic star formation rate. This project's been a lot more challenging than I was expecting so far. We've run into a lot of numerical hurdles, and currently the one we're facing is related to that AGN question I raised earlier. So the galaxies here that have exceeded that maximum mass that supernova can regulate have now started to form runaway bulges. And this in turn has made the gravity calculation very, very expensive. Because these bulges are so dense, the depth of the tree has to become very, very high. And so calculating gravity has become the dominant cost. So I'm working currently on a solution of stellar de-refinement, where we're actually merging high density old star particles in order to reduce the depth and the cost of gravity calculations. This is a thornier problem than you might think. Conserving things like mass and linear momentum is trivial, but you also want to make sure that you conserve the velocity dispersion so that you don't end up removing support from this bulge and making your problem worse. You can see with just a crude test of removing the densest stars, you can end up getting a speed up of 50% or more. So this is a tool I'm actually building into Chang'e for stellar de-refinement. And hopefully in the next few months, it'll be ready for prime time. And if you have this issue, you can use it too. So just a few thoughts before I conclude on where I think things might go for the next couple of years. One thing in particular is more feedback. So supernova feedback is just one mechanism of many. So a key thing that is obvious that we now have the ability to start doing is UV or radiation feedback. And I believe Bernhard's going to be talking more about that. Stellar winds would be trivial to add, and if we're going to higher resolution, may be really important. I'm currently working with Michael Tremmel to adopt his AGN model to use superbubble feedback as the way of treating that energy injection. And maybe even now we have the tools ready to start doing cosmic rays with the SPMHD method that Rob Bissing talked earlier about today, as well as a cosmic ray model. We could be considering adding that as another possible thing to study. On top of that, there's potentials for algorithmic and conceptual improvements. So James has been working on improving how we treat conduction because it can, in some cases, lead to sort of punishing time step constraints. And on top of that, mixing by conduction, evaporation, isn't the only possible mixing mechanism. There's been a number of recent works suggesting that turbulent mixing layers may be really important. And so the next generation superbubble model may be able to take this into account as well. So if I leave you with some conclusions, it's these. Superbubble feedback is here. It's free to use. It's ready there in Gasoline 2 and Chang'e. It can give you realistic galaxies up to L star with full metal cooling and without having to crank up your feedback energy beyond 10 to the 51 ergs. It produces these galaxies by driving buoyant outflows, and that superbubble EGN feedback is on the way, ready for next generation volumes and zooms. So if you have any questions, I'll be happy to try and take them now.
All right, great. We have time for a question or two. Jillian?
Hi, Ben. This is Jillian Bellavery.
Hi, Jillian. Sorry I couldn't be there.
We all miss you so much and hope that you're feeling all right. My question is about the stellar de-refinement. Mm-hmm. I just wrote what on my notes. So, but so are the mega bulges that you're getting, are the densities realistic? Like, this almost reminds me of what you said in the beginning of your talk about how in ancient simulations we had too much bulge, and now here you are with a whole bunch of bulge again. And so is it realistic? Is it bad? Is it like, does this really need, I don't know, what? Can you just talk more about it? Okay. I don't know what my question is.
Is it realistic? Okay, here. Is it realistic? No. Is it bad? Yes. And the reason is ultimately these couple of galaxies here. So this whole volume, the expense is being dominated by these galaxies. And the reason we're getting to this situation is this first volume was supposed to be one of three, where we're comparing, essentially looking in more detail about this question of how supernova to AGN feedback transitions. And we wanted to be able to have, here is a volume with thousands of galaxies with supernova alone. Here is a volume with thousands of galaxies with supernova and AGN. We know already from MUGS 2 that the more massive galaxies are going to have runaway bulges. They're going to produce too many stars unless you include an AGN model. And so this run that doesn't include an AGN model, we know that these galaxies are going to go bad by redshift 0. The surprise is that they go bad in a way that is also extremely numerically expensive to deal with. So the de-refinement is kind of a bit of a Hail Mary in terms of trying to get this thing to run to redshift 0 so that we have a large population of galaxies, many of which match observed scaling relations, some of which don't, which we can then look at exactly what physical mechanisms occur as they move away from them, and eventually as we can compare it to a volume run with superbubble modeled AGN feedback. So yeah, it's bad. They're not physically realistic. We knew they wouldn't be physically realistic going in. We were a bit surprised that they were also going to be so dang expensive. Yeah.
Okay, we are out of time for questions. Sorry, I know there are lots of questions. Also in the chat, feel free to contact Ben.
Yeah, I'm happy to follow up on the Slack as well.
Okay, awesome, great. All right, our next speaker is Logan Proust.
All right, hi everyone. My name's Logan Prust. I just finished up my PhD at Milwaukee, and I'm going to be derailing this Galaxies meeting to talk about binary stars for a little bit. So I work with the Astrotheory group at UWM. You'll hear from a few of them later on. And then on Friday, Phil Chang is going to be giving a tutorial on the code that we use. So since this is the code portion, I'm going to talk about some of the functionality that we've been adding to the code. I'll start with just giving an overview of some of the simulation methods that are common in astrophysics and talk about common envelope evolution, which is the arena that I've been using to implement some of these new functionalities into the code. I'll start off talking about the inclusion of a tabulated equation of state, then moving boundary conditions, and finish up with MHD. So some of this was covered pretty excellently yesterday in the Changa tutorial, but I'll go over it briefly here. There are a couple of different methods that are common for hydrodynamic simulations, one of which, of course, the one that Changa uses is SPH, where the fluid is broken up into a collection of particles. This has the advantages of being fairly computationally cheap, so you can use a lot of particles and having good conservation properties. And then on the other hand, you have Eulerian grid codes, where the space is broken up into a mesh. This is good at modeling discontinuities, but it has trouble with things like regions of gas that move with a large bulk velocity relative to the mesh, and it has preferred axes. So in recent years, what's known as a moving mesh code has been developed that attempts to capture the strengths of both of those methods. Here you have the gas modeled by a collection of particles, and around each particle is drawn a cell. So on each cell, you can apply the finite volume methods in the same way that you would in an Eulerian grid code. But since the particles move, you get some of the advantages of an SPH code as well. So it's very hard to draw a mesh for an arbitrary distribution of points. So Springle back in 2010 did a lot of pioneering work on developing the algorithms for a moving mesh code that uses a Voronoi tessellation, which is what you see here. And this is a way for drawing a mesh for an arbitrary distribution of points as they move, and the mesh cells can smoothly change and deform. The moving mesh code that we use is known as Manga, which is built on top of Changa, and it's already been applied to some other stellar problems like mergers and tidal disruption events. The problem that I'm tackling using Manga is known as common envelope evolution, or CEE. So the general idea is that you start out with a binary system consisting of, let me see if I can do this, a main sequence star on the right and a smaller companion object on the left. The companion can be a smaller star, or it can be something like a compact object. But so as the main sequence star ends the main sequence and begins to ascend the giant branch, it begins to expand until it overflows its Roche lobe and begins mass transfer onto the companion. And if this mass transfer is unstable, this can pull the companion into the envelope of the primary, and then you have the core of the primary and the companion orbiting each other as a binary inside of this shared envelope of gas. And because of energy transfer from the binary to the gas through drag, the binary tightens and much of the gas is ejected from the system. This process is thought to be responsible for the formation of many systems of interest to astronomers, including basically any close binary, including a compact object, as well as planetary engulfment. But this process has evaded study for a couple reasons. For observers, these events are fairly dim and brief, and for theorists, there are a lot of different types of physics that are thought to be involved in this system. So I've been working on trying to include some of those physics into our hydrodynamic simulations, one of which is including a tabulated equation of state, which is from the stellar evolution code MESA. This is an equation of state that's relevant over many different regions of stellar structure, and it's kind of an amalgamation of a few different types of equations of state, like the Opal equation of state and SCVH mainly. And so here's one of our simulations of the common envelope phase, including the MESA equation of state. We start off with just a giant star in the middle, and you probably can't see it yet, but there's a smaller companion object just to the right of it. And so I'm just going to let this go and we'll see what happens. And we see the companion quickly plunges into the envelope of the giant, and the binary tightens very quickly on a span of about 100 days, and much of the gas has already been ejected from the system. So an important quantity to consider here is how much of the gas has become unbound from the system. So how much of the envelope has been ejected. So we see a snapshot here from that same simulation where the black boundary there encloses all the gas which is still bound to the binary. So everything outside of that has been unbound from the system, which we define as gas having positive total energy. And we find that over just a couple hundred days, most of the envelope is ejected from the system, but we find that the answer you get for how much of the envelope is ejected depends a lot on your treatment of the internal energy of the gas. This is of particular importance because using the MESA equation of state allows us to include the effects of recombination energy. Hydrogen is expected to recombine the outer envelope, and this could inject a lot of energy into the system, which could help unbind the envelope. Though this is kind of a contentious point lately, as there are some who have claimed that the energy that is injected from recombination is quickly radiated away or convected to the surface and then radiated away, and so it wouldn't help in envelope ejection. And indeed, astronomers are saying that they're seeing hydrogen emission lines from these events, which indicates that at least some of that recombination energy is escaping and not assisting. But it was recently shown earlier this year that helium recombination, which happens deeper in the envelope, could also provide an important source of energy. So the meme really should say helium recombination instead of hydrogen recombination. We find that the orbital separation between the companion and the core of the binary decreases dramatically in just a few orbits, and it settles down into an orbit with a separation of maybe 2 or 3 solar radii. And we find that our final systems, after the simulations are done, are consistent with observations of white dwarf binaries that have similar masses and separations to what we find. Okay, now we're going to switch directions and go into moving boundary conditions. And before I talk about what those are, I'll talk about the motivation for them. So again, we have a system consisting of a giant star and a smaller companion object. Typically, in these simulations, the companion object is just modeled as a point particle, since it's so much smaller than the giant. But it's not really clear how good that approximation is. So what we would love to do is we would model all of the internal structure of the companion object, but because of the relative sizes of the two, that's just not numerically tractable, at least if you want your code to finish running by the time you finish your PhD. So what we can do instead is we can model the companion object instead of a point particle as a hard boundary, so a hard sphere, like a solid object. In particular, because of the gravitational influence of the boundary, it's expected to accrete material by a mechanism similar to Bondi accretion, and that should generate significant drag on the companion object. And it's thought that that could change the dynamics of the spiral in. So how we do this in Manga, this is implemented is we take a bunch of those Voronoi cells that we saw earlier. Instead of letting them freely flow past each other as the gas moves, we take a region of them and basically glue them together and say, okay, you are now a ball, you're a solid object, you have reflected boundary conditions on your surface, so no gas can enter or leave you, and you will all move together as a rigid body. This method is naturally compatible with moving mesh. It would be much harder to implement on, say, a static mesh, but it is possible. The boundary also moves in response to the gravity and gas pressure that it feels. And so on the bottom is one of our initial test cases where you just have a spherical boundary in a supersonic wind, and you see everything you would expect to see for an object moving supersonically. All right. And what we find when we apply this to common envelope evolution is that you find an additional drag due to the finite size of the companion object, since it's not just a point particle anymore. We've run simulations with several different sizes for the companion, and we find that as you would expect, the drag increases as the size of the companion increases. And we find that this drag does have real consequences for the dynamics of the spiraling, as we see that for larger companion objects, the eccentricity is lower. So larger companions tend to circularize their orbit more easily. This is because they experience more drag at periaps. And when you apply drag at periaps, that tends to circularize the orbit. I'll skip that for time. And finally, we've implemented magnetohydrodynamics into our simulations. So on the right, we have the Euler equations, which are the equations that are solved by hydrodynamic solvers. And in principle, it's easy to include magnetic fields into these equations. You just add another term into the momentum equation, one to the energy equation, and then an evolution equation for the B field. However, in practice, this presents some problems. In particular, the divergence of the B field, Maxwell tells us it's supposed to be 0, but numerically, due to numerical errors, it can become non-zero, and when it becomes non-zero, it tends to grow with time. And so there are multiple different ways of dealing with this. One method is simply to ignore it, but this is only a valid approach in certain problems. You can also, if an error in the divergence of the B field occurs, so if it becomes non-zero, you can sort of try to smooth out the error and advect that non-zero value into nearby cells so it can't build up anywhere. You can also include a damping term, which is what we do. And then there's constrained transport, which I won't go into right now. So in Manga, what we do, we've used the divergence cleaning scheme that's been proposed by Dedner, which includes a damping term to damp out a divergence of the B field, as I mentioned, and it uses a method of advecting away and smoothing out errors that I mentioned earlier. And I'll need to finish up quickly, so I'll skip the test cases here. But I'll finish up by saying that when we apply this module to our common envelope simulations, we find that very early on, right when the companion enters the envelope of the giant star, we see a very rapid amplification in the magnetic field energy. This is similar to what was found by Ullman back in 2016, who used not only a different code and a different MHD scheme, but also a different initial configuration of the magnetic field. So this suggests that this amplification is robust. We also see that most of the amplification happens in the toroidal component of the field, which is important because it's been recently shown that these toroidal fields within the envelope can be important for the formation of planetary nebulae after the common envelope phase has concluded. So I'll be happy to take any questions.
All right. Yep, go ahead, James.
And why didn't you let mass cross the boundary of the hard surface companion?
Why don't we let mass cross the boundary?
You were saying it accretes a little bit or something?
Oh, so it accretes onto the surface. So we don't have an accretion boundary, but like mass can still collect around the object. Putting an accretion boundary is something that's very easy to do code-wise. It's just not always clear what the appropriate choice of boundary conditions is at that surface.
Thanks.
Okay, we have time for one last question. Tom?
So in the first movie you showed, it looked like there was like an n=1 interaction between the.
Could you use your seat mic for the people on Zoom, please?
Sorry, Tom Quinn. It looks like there's like an m=1 interaction starting about now, right? It generates that wave.
Mm-hmm.
Is that, did you explore that? So it's the envelope moving with respect to the center.
Oh, the overall movement of the binary with respect to the background rest frame. Yeah.
That you see there, yeah.
Yeah, it's mostly it's just recoiling with respect to some of those bigger tidal tails. We found that is a little dependent on how we generate the initial conditions. So I'm not sure I would read too much into that as a physical result. But yeah, I mean, the first few tidal tails that are ejected are fairly large. So it just kind of depends on what direction those are ejected in.
Awesome. That is very cool. Okay. So we got, let's thank Logan again. And our final speaker, i.e. the person separating you from lunch, is Bernhard Baumschlager. So go ahead.
Yeah, don't you love it? A few large names in the community tease your talk, and you're actually not really going to talk about it. I'm sorry, James. I'm not going to go into too many details about radiative transfer. Just from the implementation side. There are some other things which I find are more interesting in 15 minutes or in 12. So if you look at the galaxy in a more quantitative way, if you take a look at the phase space, we can kind of split it up a bit in what are the regions and how are they influenced by radiation, what do we expect from them. In the upper part, we have the Hopf medium, which is pushed up there by supernova feedback, by HM feedback, and so on. And we have on the left area here the intergalactic medium, which mostly sees the uniform UV background. That's the stuff that we at the moment. That's what we can handle very well for the IGM. AGM, we have the cooling metal, which has a uniform UV background included, so that's a fairly good model. We have the super bubble feedback, which does a great job in pushing the stuff away from the fast cooling areas here. But you see there's still a lot of material left in this region. There we have the circumgalactic medium, the ISM, and the cold molecular dense phase, which all are influenced differently by radiation. The circumgalactic medium, for example, we have on the outside the UV background coming in, while from the inside we have the galaxy shining outwards. So there are two different radiation fields. In the galaxy, in the ISM itself, we are mostly dominated by stellar radiation. We have heard from Ben before that FUV heating plays a crucial role in there, but also stars in terms of the ionization state. And lastly, we have the cold, dense molecular stuff, which is influenced by Lyman-Werner radiation, which dissociates H2 molecules, or also ionizing radiations in the different bands. X-rays and cosmic rays can penetrate much deeper into molecular clouds than the UV radiation. So all of these different radiation effects point clearly towards that we need some treatment, a proper treatment of the radiation field and radiative transfer in order to get the ionization of our gas correct. So considering we want to get the ionizations right, it's a fairly simple equation. The ionization rate is the integral of the flux times the cross-section. Seems fairly simple. The cross-section is also not the problem. We can approximate that fairly well on, say, a power law. The bigger issue is the flux term here, which is very different for different radiation sources. Old stars have a different spectrum than young stars. So just as example, on the left, the Hart and Padauer UV background at redshift 15. If we just look at the black line, we see weird shape, some absorption features in there, but compared to a young star, the other side, or a young star cluster, I should say, it's a star cluster about the end of the 6 solar masses at the age of 1 million years, calculated on Starburst 99. You see they are very different. And that's the kind of different sources we have to combine. Just from two different times. If we include the factor of time, it gets a bit crazier. We have to be able to handle all of these variations at the same time by the way we treat the radiation field. So what we came up with is a treatment in 10 bands. I should have said 9 narrow bands and 1 broad band, but it's fine for this. So we have 1 band for the FUV heating, as you heard before, for the ISM. That's very important. We have 2 narrow bands, which are just 0.1 electron volts wide for each of the classical broad bands. So the Lyman-Werner bands, the one at its left edge at 11.2, and 1 band just shy of 13.6 electron volts. The same for the hydrogen ionization and the helium ionization bands, and then we have one energy of about 500 electron volts, which we need to get the early ionization from the UV background correct. If we don't include this band, we underestimate especially the helium ionization rates by about 20 to 30%. So now on this approximation, we can do something very cool. Well, should have mentioned, between these narrow bins, which are between the narrow bins here, we approximate the spectral shape as power law. And we have seen them before here. The red lines follow quite nicely the spectral shapes. So in this approximation, we can simplify this equation a bit more to a numerical manageable equation. First, we plug in our spectral approximation between in the broad band. So we have the left H1 ionizing band, for example, and the right one. We have can calculate the flux normalization and the slope that we see in this band and multiply by the cross section. Yeah, as I said, the cross section can be fairly well approximated by some combination of the power law. This second term behind there is to get a handle on the errors at the high energy side between each bin. And so we get this expression here. This guy is analytically integratable over its bands. So we have a very nice. We have a solvable equation which we don't have to iterate over during the on-the-fly calculations. But now I tell you that's a nice equation, but how does it actually look like? Is this any good? If we consider just the hard and not out background into a theoretical calculation, the black lines over here, which are very close to the red ones, are what we would expect from numerically integrating the first short equation. The blue lines are piecewise constant approximation. That's usually what is done in radiative transfer codes. You have your ionization bin, say H1, helium-1, helium-2, and you have one value of flux and one value for the cross section, which you hopefully adjust to the spectral shape. But typically it's used as one value, and that's what I did for the blue lines. You choose one value for the cross section, and you see you get large errors, especially down here up to 2 orders of magnitude. Whereas our new approximation follows the ionization rate very nice, and there's small errors all through. What is also cool, what we can do, we can reconstruct the spectra of that gas particle C. So I know I'm always getting criticized for plotting extreme ranges. We have 100 orders of magnitude here. But just to show what is possible. So on the top line here, there's one part, and that's randomly selected particles. It's about 100 different particles, so each color is a different spectrum that the particle receives. There's here one, which is dominated by a single young star cluster. Then we have here, for example, the turquoise one, which you probably can see properly, this one here, which is at the end, which is pretty much pure UV background at the verge of 0.25. Then we have all these large variations here in this probably meaningless part below. But you see all the different shapes, and that's the cool thing that we can see it, and our code is able to work on this and handle it. We still get proper ionization rates. Oh, I'm a bit fast today, that's fine. That's another very preliminary result. It's a rerun of the 7 dwarfs that Ben just mentioned before. This RT, so on the left here, we have the total gas density and the H1 surface density with RT and without RT. So without RT means we have the classic cooling metal in it, which turns on the UV, depending cooling rates, heating and ionization rates at around redshift 15, everywhere for the whole galaxy at the same time. While on the left, here, we turn on the UV background at about 15, ramp it up to the published values by turn it on at 16, ramp it up to redshift 15. And you see how the ionization propagates inward. There's some smaller differences as well in the core of the zoom-in region. So 2.5 megaparsec, by the way. In the core of the zoom-in regions, we see a bit more of a bit higher density filaments than in the old case. That's to be expected. Here it is getting ionized, but here it still doesn't see any radiation. And on the left side, we see the flux in the one of the narrow H1 ionizing bands. You can see clearly how it's moving inward. And if you're lucky, yeah, you might be able to see it. Right.
Could you please speak by the podium for people on Zoom?
So the area where I was just pointing, that you can see a little star blinking up as it moves through the slide, through the slides of the box. So all of this is, of course, run on the new RT master Trevor 2, which is a successor of Trevor 1. And yeah, wrong one. Very cool code based on Trevor 1. As I said, it works at servers and sources at the same time, and we get incredible and active log n, the log2n costs for it, which is absolutely amazing. And at this point, I have 1.5 minutes left. So I hope I convinced you that we need some sort of radiation treatment in order to get our galaxies correct. And that our new approximation is a great way to combine sources and to accurately calculate the ionization state of the gas. On this note, thank you very much. If you don't have too many questions, we can enter the lunch break fast.
All right, great. Do we have some questions? Yep, go ahead.
Okay, mic's working good. Hi, Bernard. I'm Parek. I work with James. I had a question about the 10-band approximation you have, namely, why is there a low and a high for each of the 10 bands? Why not just have one Lyman-Werner band and one H1 band?
That's essentially how. If you have it's one way. If you just have one band for each of them, you end up on the blue line here. That's essentially the issue. There's also another thing that you can see over here, that there are massive jumps at certain redshifts from left to right of your ionization edge.
Right.
And on placing two bands next to each other, we can capture these jumps. If you have just one band, you wash out the stubs.
Oh, I see.
And also, if it's continuous, you see the red line follows the spectrum while you have jumps in the blue line.
Yeah, I see that. Okay, good, thank you.
All right, any questions online or over here? Tom?
Interesting work. How do you handle boundary conditions? Can you talk about that?
Boundary conditions for radiation is just outflow. So we don't consider periodic boundaries. It's mostly for zooming cases, so you don't have anything else around. And the radiation you would see would just be your own light again.
All right. Any last questions?
I guess people are hungry.
Okay, thank you so much. Let's do one last big round of applause for all our awesome speakers.